In this live example, we're going to simulate a battle, or in particular, one attack in a made-up video game, Legend of Groöl. So in this scenario, we are playing a BattleMage, and we have a 15% chance of missing when we attack our enemy, in this example, the Grimthurst Ogre. The Ogre is using a shield, so the Ogre has a 10% chance of blocking our incoming attack. So both of these are going to be event-based elements in our simulation. If we are able to strike the Ogre, that is if we don't miss and the Ogre does not block us, then our weapon is going to deal a random amount of damage taken from a normal distribution. So we're going to do a mean of 60 damage when we hit with a standard deviation of 5. On top of that, if we successfully hit, we're going to have a 20% chance of doing double damage with a critical strike. So these are just some of the elements that are often incorporated into games, RPGs, or other types of games that are all based on chance, either event-based chance or some distribution of chance, and are going to mirror things you see in tabletop games like rolling dice of different amounts. So in just this scenario of us attacking this ogre, what we're interested in is looking at what's the histogram of the damage we are going to deal based on all of these random events happening at the same time, of the possibility of us missing, the possibility of it being blocked, the amount of damage we could deal, and then the possibility of being able to do double damage. So what does that distribution look like just on our attack on the ogre on this round? And then on average, with all of this happening, what's the average amount of damage we can expect to deal to the ogre? Now, if we were actually making this game, we would probably not use MATLAB, but the random elements and the analysis of what's going to happen, we can do in MATLAB using different types of random elements and then putting them all together. As a note, this is a live example, so I have not solved this one before, so you will be coming with me on the journey of coming up with a solution for simulating this attack and then coming up with a histogram using a Monte Carlo simulation. Since any one attack is going to be, the result of it's going to be dependent on all of these random elements coming together, we're going to need to repeat the attack over and over and over again to come up with a distribution of all of the possible ways that the attack could be resolved, because of the 4 things in this that are going to have random elements: the possibility of us missing, the possibility of our attack being blocked, the amount of damage we deal if we successfully strike, and then the possibility of dealing double damage. All right, so I copied in the text here and just initializing with clearing everything out, so I'll write this just as a script. All right, I just want to first simulate this working for a single attack and the possible damage we're going to deal there. Then I'll worry about repeating this so that we can get a distribution and an expected value of an attack, taking all of these random elements into account. All right. And again, there's going to be a lot of different ways we can put this together. So the one way that I'm going to pursue is not necessarily the best, and certainly not the only way that we can do this. So I'll start by just taking the text in order here, in putting all of these different elements together. All right. So first, we are going to have a chance of missing when we attack. So I'll just call that miss. Now this is what I'll call an event-based element here. There's just some probability we are given a 15% chance of missing. So what we can do here is I can come up with, I want to develop some random element and then assess it so that 15% of the time that I run this, I am going to note that as a miss, and then the other 85% of the time would be a hit. This is before we worry about the shield blocking us. This is just the possibility that we completely miss the target. One way that we can simulate this element, this event-based element, is we are going to use rand here. So remember that rand is going to give us a number on a uniform distribution between 0 and 1. So every time I run rand, I'm equally as likely of selecting any decimal between 0 and 1. So how can we use this to our advantage? When something like this probability element, where in this case there's only two things that can happen, we hit or we miss, but we could have 3 possibilities, 4 possibilities, but all the possibilities are, we have some probability assigned to it. So in this case, I'm going to create a number between 0 and 1 at random with a uniform distribution with rand. And what I'm going to say is if rand is less than 0.15, then I am going to say that miss is true. Now, this probably won't be the best way to do it. I'm going to actually do this differently. I'm going to say that if rand is less than 0.15, we hit. And we'll see why in a second. I think that using hitting instead of missing is going to be a little bit better. And otherwise, it's, so this is we miss, and this is we hit the target. So again, what is this doing for us? Every time I run this, so let's just see for testing purposes how often are we hitting? Well, it should happen 15% of the time. I'm sorry, we should hit 85% of the time and miss on 15% of these runs. So I am running this over and over again. So that one was a miss, and I'm going to keep running this. So I'm not going to run it over and over and over again, but this should yield that we hit 85% of the time, and the hit will be 0, indicating a miss 15% of the time. So this section will be hit or miss the strike. All right. Now, so that's 85% of the time hit should be a 1, and 15% of the time it should be a 0. So now I want to count for, are we blocked by the shield? Right, so this is another element-based probability or event, or event-based element. So we are told that 10% of the time the ogre should block all of our attack. So we're going to deal no damage, even if we hit 10% of the time the ogre is going to be able to block. I'm going to assume for this that it's not 10% of the time we strike there's going to be a block, but 10% of any time we attack there would be a block. So even if we miss, I'm going to say that it's possible that we miss and the shield would have blocked us. So there is a difference there. It actually decreases the amount of blocking that would take place, but basically what this is saying is that us missing is independent of the shield blocking. So that's why this is going to be a completely separate if statement and not dependent on if we hit. All right, so separate element here. So I'm going to make a new random number. So this rand will be different. And I'll say if it's less than 0.1. Oh, and as a note here, because it's a uniform number between 0 and 1, there's basically 0% chance it's going to exactly be 0.15. So that's why I'm using strictly less than here. If I put equals with a rand here, it really doesn't make any difference because the chance of it being exactly 0.15 is basically 0. So I'll just stay with a less than here, but whether I put a less than or an equals, really the same idea. All right, so does the shield block us? So again, 10% of the time, rand should be a number between 0 and 0.1. So in that case, block will be, again, I want this to, as we'll see in a minute, be the opposite here. I'm going to set this to instead pass. All right, so so this is shield blocks us. And otherwise, that means that rand was greater than 0.1, so I can use an else. I could put else if greater than 0.1. It's going to be the same thing because there's only 2 possibilities for the shield. It either blocks our attack or it doesn't. Again, if there were 3 things that could happen, maybe there's 10% of the time it'll completely block our attack, 10% of the time it'll cut it in half, and 80% of the time it does nothing. Well, then we can have separate else ifs that would happen, but in this case there's only it completely blocks it or completely goes through. All right, so 90% of the time pass will be a 1, means attack goes through. And here I'll display pass is what I used. Again, I'll address in a moment why did I assign 0 for the event occurring. Either we're missing or we're blocking, but really that's just the opposite of I'm going to say that hit is the event. So 85% of the time we do strike, and 90% of the time the shield does not block us, or it allows our attack to pass through. All right, so if I keep running this, we now have these two independent events. So most of the time we should strike, and most of the time the shield should not block us. But here we see a 0 for pass, so we did hit, but the shield blocked our attack. And if I keep running it, this time we completely missed, but had we not missed, the attack would have gone through. So I'm going to get rid of these displays for now. It's so far working correctly. Now, I could put some if statements here that, like, it doesn't matter how much damage we would deal if we either missed and or the shield blocked our attack. So we wouldn't even need to necessarily assess how much damage we're going to deal if it wouldn't matter if we missed our attack. But I am going to, every time, see how much damage we would deal, and we'll see why I can do that in a second here. So I'm going to make a randn. This is going to be damage dealt. All right, so this will be, I'll call it damage. I'll call it DMG1, as we'll see why I want to do that in a second, because our total damage could get modified because of a critical attack, or all of our damage could get blocked. So I'll save DMG for the actual damage we're going to deal. All right, so it's going to be from our weapon, we're going to do, it's going to be a random number coming from a normal distribution with a mean of 60, a standard deviation of 5. So what we can do is 60 plus 5 times randn is going to, again, if I keep running this, every time I run it, I get a different number here, but it's going to have, on average, it'll be 60. It's, again, coming from a normal distribution, and this ensures that it's always going to come up correctly there. So that's how much damage we deal. That's, again, what I'm calling DMG1. And lastly, the last random element, again, notice hitting or missing, the shield blocking or not, those were these event-based probabilities. I'm using rand for that. The damage is also a random element, but this is a continuous number coming from a normal distribution, mean 60, and standard deviation of 5. And now the critical strike, that is back to, again, this event type of element here. So it says that 20% of the time we have a chance of critting. So here I'm going to use that rand again. So if it's less than 0.2, and that will happen 20% of the time I run this, crit is going to be true. And else, crit is 0. And actually, I'm going to modify this. I'm thinking ahead here how I want to use this. So I'm going to actually make crit equal to 2 if rand is less than 0.2. So crit is going to be 2 20% of the time, and 80% of the time we do not crit. And I guess I'll show this two different ways. This is going to be a more compact way, I think, of assessing how much damage we deal, because I'm going to say that the total damage we deal is going to be DMG1, so that's how much we strike, times crit. And actually, I'm going to also multiply by hit and by pass. All right, so let's see why I can do this. The way I set up my variables, again, I'll show another way in a second where I think it might be a little bit more straightforward, but a little bit less compact. If I miss, hit is going to be 0. And if I do this multiplication here, I'm going to have a 0 times, and it doesn't matter what the rest of this is, I deal no damage. Same thing for shield. If the ogre blocks us, pass is 0. So pass is going to be 0. When I do this multiplication, it doesn't matter how much damage I would have dealt, I will deal no damage. So DMG, the actual damage I deal, would be 0. Okay, let's say hit is true, so it's a 1, pass is true. Now I care about how much damage I would deal. Well, I'm assessing that in 41 here. All right, so that's going to be however much it is, so it's 1 times 1, so that doesn't affect our multiplication, times the amount of damage. And then finally, if we crit or not. So if we crit 20% of the time, it's 2, so I'm going to multiply the damage I deal by 2. And if I don't crit, then crit, the variable, is 1, so it also doesn't modify my damage. So this is a really compact way that I can represent this whole scenario here. The DMG, the total damage, is 0 when I miss and or when the shield is blocked. And if it's not blocked and I do strike, well, then it's just 1 times 1. It doesn't affect it. It's just the damage I would have dealt. And then the crit doubles it when I crit, and it just preserves it at 1 when I do not. So that's one way I can assess my damage. All right, so let's see here. I'll just display it for testing purposes at the moment and keep running this. All right, so those are going through and I'm not critting. Keep running it. All right, in this case, it looks like from my workspace, I actually missed and the shield would have blocked it anyway. So I dealt no damage on that attack. Right, that time, it looks like I just missed the attack. I want to see one where it crits. Okay, so that should come up sooner, but all right, and this one, the random for the crit was between 0 and 0.2, so we see crit was assigned a value of 2. We did strike, we were not blocked by the shield, so we dealt that extra damage, so we dealt 117 damage because of that crit. All right, so everything appears to be working correctly. So let me change this a little bit. I think this is a more compact way to do it, but let me do it in, I think, a little bit more obvious way. If you were a beginner programmer thinking about this, I'm going to say miss. Right, so it might be a little bit easier way to think about it. And I'll use if statements here. And I'll change my variables also, so I think it's, again, a little bit more obvious. Okay, so I changed this a little bit. So now I'm going to be 15% of the time miss is true. Here, 10% of the time, I'm going to call it block now. Block is true or block is false. All right, so I'm going to do that first. And I'm going to say I don't even need to worry about damage if I miss or if I'm blocked. So if miss is true or block is true, the damage is 0. And it wants me to use a double here. Okay. All right, so if I miss, so if miss is true or the block is true, I've dealt no damage. All right, otherwise, now I can worry about, well, the order I do this in, I'm going to do this as a, now I can worry about critting, because it doesn't matter if I critical if I miss anyway. All right, so let me move this actually into this else statement. So I only enter this else statement if I've not missed and I've not been blocked. So I'm going to do nest my crit in here. All right, so now I'm going to change this to, again, just this binary, I do crit or I don't crit in this case. All right, so in this chain, I've not missed, I've not been blocked, so now I'm going to make a random number. 20% of the time crit is 1, and 80% of the time crit is false. And let me indent this a little bit more. I have an extra end here. All right, now I am going to assess how much damage I would naturally do. And now I will say if crit, so if crit is true, then the damage I deal is twice DMG1. and else the damage ideal is just DMG1. And I'll modify this. Okay, so this should do exactly the same thing I was just doing. I think the logic is a little bit easier to follow this way because we have this if statement here. So right here, does attack go through is really the first question for the if statement. So in this case, no, the attack did not go through. And here, attack does go through. So the way I set it up in this new structure here, we only even worry about damage if the attack goes through. We only worry about critical if the attack goes through. So it's if we go into this else chain, we worry about criticaling, we assess how much damage we would naturally deal, and then we're going to double it if we criticaled. So let me just run this a couple of times. And we should be getting, I didn't test it against what I did before, but we should be getting exactly the same results, just in a little bit different way. Right, so I'm running this. So again, this time, in this time we missed, so it just automatically went to 1. In this time, we did not miss, it's false. We were not blocked, we did not get a crit, so the damage we dealt was just that DMG1. All right, so I just wanted to go through this to see there's alternate ways we can do this. That might make sense. And actually this way with the if statements is probably a little bit more flexible too. If there were other types of random events that could be occurring, they're going to modify the damage we deal either up or down, then maybe using if statements is a little bit better than simply multiplying it together. But a lot of times with these independent events, multiplying is how we can have them all happen at the same time. Okay, so we are able to now every time we run this, it is simulating a single attack that we have on this ogre. So what we want to do is, since there's 4 random things happening simultaneously, this is a time we want to use a Monte Carlo simulation because we can now run this thousands or a million times, millions of times to see, all right, what does the distribution of the damage we're going to deal look like on this ogre? And we're going to see on average, how much damage can we expect to deal? And really that's just when we look at the average amount that we're going to have. All right, so I want to wrap this in a Monte Carlo simulation like we've seen before. I'm going to start it small. I'll just do it for 10 times to make sure it works. All right, and I'm going to, I don't need to display that anymore. And I'm going to indent with a Control-I on my PC. And what I'm going to have is, I'm going to make this master list. I'll call it capital DMG. And that's going to initially be zeros, the number of SAMPs by 1. All right, so I just want to pre-allocate here. And what I need to do is once I assess my damage, then DMG of K, I'm going to save how much damage I dealt in that case. All right, so let me just run this. All right, so I only ran it 10 times for right now, so I can see what's happening. Sorry, I ran 100 times. It still runs pretty fast here. And I have a whole list of numbers here. So this one's going to be a little bit different than some of the other simulations we ran because we have a lot of zeros in this, and then we have other numbers as well. So we might see the convergence. I'm expecting it might actually take a little bit longer because it's not going to be nice and as continuous as we've seen in some previous examples here. But we do want to check convergence just like we've done before, and we can do that by checking what's the average value of capital DMG as I keep adding more and more simulations to this. So it's that kind of running average that we've seen before. So I'm going to do this as a semilog in X, and I am going to look at DMG, or the cum sum of DMG divided by 1 to SAMPs. And I might have this, let me just check to make sure everything is the right orientation here. This is a column vector. This is a row vector, so I do want to transpose this so that I'm doing a column vector divided by a column vector. Otherwise, the sizing is not going to be right. Okay, so that looks good. All right, so again, I'm looking at the running average of capital DMG as I keep adding more samples. Let me run the whole thing here. Okay, so I would say we've definitely not converged yet. We don't see that nice flat area that we should expect. And I've only run it 100 times, so we shouldn't really expect that to happen. So let me just put in some labels here so we remember what's going on. So capital N, that's just the number of times I'm running the simulation. And my Y label will be average damage in hit points or whatever we're using here. And here's my figure. Okay, so I need to run it more times. I've not yet converged. I can't really give a good estimate of how much damage I'm going to deal on average. So the histogram I would make with this data isn't going to be the full picture yet, and the average is not going to be really correct yet either. So let me increase the number of samples I'm running this. Right, so I'll just go up to 100,000 and see what that picture looks like. Right, so it did run pretty fast. So we see here, okay, it looks like it's actually pretty close to converging. I thought this would be a little bit longer to converge. Let me just run it 1,000,000 times just to make sure. All right, so we see here that kind of telltale flat amount or the flat area that we have. Definitely about like 100,000, and it's really flat even out to 1,000,000. We see that, yes, this was enough samples to run. We have reached convergence here. So this is actually going to answer the second part first. How much damage do we deal on average? On average, we can expect to deal 55 damage. Right? That's because here we have a decent probability of just outright missing or the shield blocking us. So even those extra criticals happening aren't really increasing the amount of damage we're dealing on average. So on average, we're actually dealing below the mean value that our weapon should be doing here. Let me just as an experiment see what happens if crits do nothing. Right? So if we can't crit, I'll just temporarily change this to 1 to see does the probability of critting really increase or increase the amount of damage we can expect to deal. So let me run this again. So I guess so, yeah. So the critting does, if we didn't have crits, we would expect to only do 46 damage on average. Let me go back. Compared to with critting possibilities, we're going to deal on average. It's still pretty flat there. Let me actually run this a little bit more. It looks like it's not necessarily converging. I'll run it 5,000,000 times just to really be sure here. And down here, I want my axis to be tight. All right, so again, this is with crits again. I put that 2 back in there. And we're at roughly 55 damage on average. So the second part of the question we can answer, on any one attack, we can expect to deal on average 55. Now, an average here is a little bit tricky because there's a lot of times we're going to deal 0, and then if it goes through, we're going to be dealing then the 60 plus or minus 5, that standard deviation there. But that's what we can expect is on average for any one attack, we're going to deal 55. And I expect the histogram for this to look kind of odd because it's kind of good to jump. A lot of times we're dealing 0, and then we're going to see this distribution around 60, and then we're going to see a little bit, again, uncommon. We're going to have damage around, I would guess, like 120 for the times we crit. So this is really going to look different than the histograms we've been seeing before. I'm going to do this as a separate figure. And I'm just going to here explicitly put figure 1, even though it would do that naturally. All right, so in figure 2, let me look at this histogram. And notice I'm using the histogram function here rather than hist, but I could do it either way. All right, so we see here kind of a wacky histogram happening. A lot of attacks we're going to deal 0 damage because we miss or they're blocked. These are the ones that go through, but we do not have a critical strike. And then over here, this is where we're doubling our damage due to a crit happening. So we have kind of this discontinuous histogram that we haven't seen before because of these discrete type of things that can happen, that there's ones where it just wipes out our attack, or times it can just jump and double the attack, as we see here. All right, so in this case, this is what the damage distribution can look like. Now, this would be important information to know from either one, if we are designing a game and we want these random elements and we want to think about, and when we're designing it, well, what's a fair amount of damage for a weapon to deal? Or what probability should we put for how often a shield blocks or how often we miss? And what we can do, like I was doing before, I can change that value of the crit. I changed it to 1, but we can play with a lot of these parameters here to make sure that when all of these random elements are happening, and then we look at the distribution that we might be interested in, to make sure it looks fair. Because what would we not want if we're designing a game? Well, we don't want to just have something super overpowered that crit is doing like 100 times your damage, because it's going to skew the amount of damage we're dealing so far. Let me just show what would that look like if a crit was so overpowered that it dealt 100 times your normal damage. Well, look, it kind of like blows out the normal. We sometimes are dealing just a lot of damage there, and we're seeing that in average attack now, on average, because the crit is so high, we're dealing almost 1,000 damage, more than 900 damage on average. So that's probably something where no, crits are worth way too much. Or we could have something where we have the ogre can block 80% of the attacks. So let's change that and see what the distribution looks like. Well, again, one, it's going to bring our average really low. On average, we're only dealing about 12 damage. And the histogram here, so often, this is not a relative frequency histogram. I should do that, actually, since I'm using this histogram. So I actually forgot off the top of my head, so we'll go through this and remember how to... histogram has more built-in options than hist does. If I remember correctly, we need to set this up for a probability. Oops, I want to search within histogram. Here, normalization and then probability is what I want to put in for my options here. So this will make it a frequency normalized histogram, which is typically what we want to look at. I think I'm spelling that wrong. I'll just copy and paste so I don't make an error. All this does is scale the y scale here. Normalization. Oh, I forgot to end the single quotes. Okay. All right, so now this is really a percentage of the time. So here, over 80% of the time, we deal no damage, and then we're dealing some damage here less of the time. So if we assessed this, we would say, you know what, this is really unfair for the player. That ogre just blocks way too often. So let's just set that back down to 10%. And relook at the histogram here. All right, so we could assess this and from a design perspective say, yes, this is a fair distribution. We're going to block some, well, even here we're missing, we're dealing 0 damage almost a quarter of the time. But there are times we're dealing this extra damage here, but we still might tweak it and say we need to miss less, we need to block less. We don't want the player having that many misses. It's not fair. Or if we're from a player perspective, we might if this is some sort of role-playing game, in how we design our character to optimize our performance, we could put these types of values in and simulate our battles to see, well, how much damage do we think we're going to be dealing with on average if we put in different weapons or different modifiers into our character. So there is a lot of application to this, but this was a good example with actually combining these event type of elements, things that in this case were binary conditions, we hit or we miss, but could have more types of possibilities there. And then we also have the drawing from a distribution, like we're dealing with the damage. Well, that's coming from this normal distribution with some mean and some standard deviation built into it.